Welcome to the last lecture in the functional programming paradigm. Today the topic is about higher order functions. Okay, let me recall a few, let's say, concepts we took a look at the previous lectures. The first one is about currying. What I want to do is I want to implement a function that performs the addition of two numbers. Thus, the addition of xy is equal to x plus 1. A simple one. Okay, thus the add, just let me repeat what I did so far. Okay, the add will be a function that will be applied on one argument. It returns a function. It's a curried function. That means the add x will return a function that will be applied on another argument, and the whole thing will give me, let's say, a result which corresponds to the addition of x plus 1. Once I will go and I will, let's say, compile, and after that I will run it with 5 and 6. This one actually will work perfectly and the addition will be performed. If I perform the addition of 7.2 and 3.1, then the result will be equal to 10.3. That's clear. Once I will be asking about the type of the add, it will be a function that takes as an input one parameter. It's of type A. The A is of a numeric value. It returns a function that takes as a parameter another value. I'm talking now about the y. Okay, the y has to be of the same type as the x, and last but not least, the result will be the addition of x plus y, where the type of it will be actually of a numeric value. Okay, now I will go and I want actually to implement the successor of a number x. Now you will see that actually I could have different definitions of this case. Successor of x is just to increment x by 1. Thus one of them is just to write successor of x is equal to x plus 1. Okay, I will go here, I will load, and the successor will be working actually perfectly. If I have successor of 5, it's equal to 6. And if I have the successor of 4.1, then actually the result will be 5.1. And that's why if I will ask about the type of successor, then the result in this case is the following. Okay, the successor actually takes as a parameter a value of type A. The A is of a numeric value, and it performs the addition of x plus 1. Okay, thus in this case, the result will be also of type A, which is a numeric value. Okay, now instead of doing that, I can actually think about the following. I will go here and I can think about using, in this case, the function that I defined before, which is the addition. Thus, the successor of x corresponds actually to the addition of 1 and x. Okay, thus once I will do it, once I will go here, and I will compile, and I ask about the successor of 4.1, this one will work, and if I will ask about the successor of 5, this one will work too. And the type of the successor is the same as before, which is a function that takes as a parameter a numeric value, and what it does is it returns actually here the addition of 1 plus x. If you take a look at the type of the return value of add xy is also of a numeric value, and that's why you get here also as a result a numeric value in this case. Okay, now let's look at curried functions. The nice thing is what I can do is here is just to remove the x from the left hand side and to remove the x from the right hand side. Thus what I am doing here is I am defining a function successor as a function which is add 1. Okay, really nice, really, let's say, compact, concise, and the implementation is just to define a function, okay, by saying that the successor function is a function which is defined as add 1, because the add 1 will return a function that expects as, let's say, a result another function that takes another parameter to return actually the result of x, in this case the x plus 1. Okay, here is the same. That's the add one will return a function that expects a parameter, and this parameter will be taken to perform the addition one plus this parameter in this case. Okay, now look, once I will do it, it looks really nice. Okay, it works, and if I do actually the successor of 5, then the successor of 5 will be equal to 6. Okay, now the question is, why doesn't it work if I will do successor of 8.2? Okay, because the type of the function will change now once you define it in this way. Okay, the type of the function has something to do with the type of this literal, 8.1. Okay, in this case, Haskell will know exactly that this literal is of type integer, and that's why the type of successor will turn actually into a function that takes as a parameter a value or an input of type integer, and the result will be of type integer in this case. Okay, now the question is, if I wouldn't have had the add one and I want to define, let's say, the successor one. Okay, now you will tell me you can use the operation plus. Okay, that's what I will be doing here is I will be writing something of the following form, that successor is equal to plus 1. You will go here, you will load, and what you will get here is successor of 4. This one will give me 5, and then I will take actually successor of 5.1. You get actually the same one. Okay, the same let's say error. Why? Because the type of successor, even in this way, is of type integer, implies integer in this case. The question is, what is actually plus 1? The plus is the operator, is to perform actually the addition of 1 with something else. Okay, and this something else is, let's say, the parameter of the successor function. In this case, if I have successor of y, then the y could be equal to, in this case, 1 plus y. Now, what I will do is, I will remove this one from the left-hand side. I will remove this one from the right-hand side. And what I do is, I return this one into a function, okay, which is an operator plus that takes as a parameter an integer. It returns a function that expects, in this case, another integer to perform the addition of, let's say, the one with this parameter in this case. This is, let's say, the beauty of querying. In this case, you can define a function using another function without writing explicitly the parameters of the function in this case. Okay, good. Let's move on. And let's take a look at the following example. What I want to do is I want to write a function which is called sum all. Okay, I will just give you an example what this function actually should do. It takes 1, 2, 3, 4 as input, and what it should do is it should return for me, let's say, the result 2, 3, 4, and 5 in this case, meaning it should take all values one by one, okay, of the list, and it should increment every value by 1. That's what I will do is I will go to the sum all. Okay, this one will be equal to an empty list. Okay, and then the sum all of a list that consists of two parameters, one parameter, which is a list x dot colon xs, which is a list that consists of at least one element. And what I will do is I will take, let's say, the x, I will increment it by 1, and what I will do is I will const with the result of summing all of xs in this case. Okay, most probably once you will compile and you will just call the sum all of a list that consists of 1, 2, 3, 4, the result will be exactly the same one as you see in our file here. That means if I'm having 1, 2, 3, 4, okay, then the result will be 2, 3, 4, 5. Okay, a simple one. We have already seen how to write functions that deal with lists in this case. Okay, if you want actually to take a look at the type of the sum all, okay, then in this case I will be having something of the following form. It's a list of type A, where the A is of a numeric value, and the result is a list of type A. okay, where the A is, let's say, also of numeric value. Meaning, what I can do is I can take the sum all and apply it on something of the following form: 1, 2, 3.4, and 4. Everything will turn into floating point numbers because the 3.4 is of a floating point number in this case. Okay, now what I will do is I will go and take actually the product all. Okay, now please actually look what I will do. I will just do the same thing. The product means it takes actually a value, well, I will call it twice all. Okay, twice all means I will take actually every value and it has to be doubled. Thus, if the list is an empty one, then the result will be an empty list. If the list is not empty, okay, twice all, okay, XS, it's a list that consists of at least one element. What I will do is I will take, let's say, X, multiply it times 2, okay, and I will consist with twice all. Please look at the sum all. It's almost identical. What I am changing is here only, let's say, the name of the function, and last but not least, the operation that I'm performing here in this case. Okay, and once we will do it, if you will go and you will run it with twice all, 1, 2, 3, 4, what I will be getting here as a result is 2, 4, 6, 8. It works and it's really nice. Now, the problem here is I know exactly that there is a kind of pattern where the only thing that changes is the following, which is the operation that I'm performing here. Okay, thus the question is it possible to implement a function that takes as a parameter a function, where the function is the operation that I will be performing on every element in this case? Okay, that's the function. I will call it map2, where the map will take as let's say parameter a function. Okay, and what it does is it should just get another parameter, which is a list, and it performs this f on every parameter of the list. Thus, if the list is empty, then the result will be an empty list in this case. However, if I will be having map to f, it's a function that should be applied on all parameters in this case. Thus, I will take the f and I will apply it on x, and that's why the result will be here in this case f of x. Okay, now please look at the pattern. I'm having x plus 1, x times 2, and here an f which is applied on x. And what I will do is I will consist, okay, map to f and xs in this case. And the nice thing is, once I will compile, okay, now what Haskell will tell me is, yeah, I will accept it. And the nice thing is, if you think about, let's say, the map2, and take a look at what I wrote here, okay, I will write plus 1. It's a function, okay, that performs, let's say, a kind of an increment of a value by 1 of a list 1, 2, 3, 4. Okay, the result will be, in this case, 2, 3, 4, 5. If I want to do the map 2, and instead of, let's say, the addition by 1, you multiply times 3, then the result will be 3, 6, 9, 12 in this case. If you take this one and you divide by 2, okay, then in this case the result will be 1 divided by 2, which is 0.5. Okay, 2 divided by 2 is 1.0, and so on. Okay, thus it's just actually a function. Okay, and now we want actually to find its data type. Okay, now I will do it actually step by step. I will look only at the first line. Okay, thus the question is, what is the type of map2? Okay, now let me look at the type one by one. I see an f, okay, and from only this this definition, I can only say that the f is something of type A. Now I see here a list, Okay, that's the only thing that I can do is I will say this, the whole, actually I will write actually the pattern is A implies B implies C in this case. Okay, the A corresponds to the F, the B corresponds to this list, and the C corresponds actually to this list in this case. Okay, now this is the pattern of the type. Now I will do it actually backwards. If I take a look at this list, that means actually the parameter, the value B has to be actually of type list in this case. And now since I am not having any values, okay, I cannot say anything about the result except that actually the result is of type C. Please actually look that I am considering only the first definition of the map 2 just to deduce the type of map 2 in this case. And I will go and take a look at the second definition. The question is this data type the data type of the result, or okay, will it be more, let's say, specific in this case? Okay, now let me go to the left hand side. If I see here an F, then this one will remain A, because actually I do not have any information about how the F will look like. If I see X colon XS, then in this case I know exactly that the data type here, it's a nice one, it's a list of values in this case. Okay, now let me go to the right hand side, and what I will see on the right hand side here is that the F is applied on X. Okay, meaning in this case I will know exactly that this data type is a data type of the following form. The X is of type B, okay, because here I'm saying is a list of X. Okay, that's what I will be having here is I will be having B, okay, and I will be applying on the B, let's say, something that will give me a result that will be having as let's say pattern the following, that F of X is the first element of the result list. Thus I know exactly that this one is of type C. Okay, thus I will be having B implies C implies a list of B's, and the result is a list of C's in this case. Okay, now look, once I will actually get the type of map 2, it gives me the same pattern. It's A implies B, okay, where the A implies B is the data type of F, the list of A's is the data type of this parameter, okay, or X colon XS, and the data type of let's say the result is the data type of B, which doesn't need to be of the same data type. Now the question is, let me think about an example where the input will have a specific parameter and the output, or specific data type, and the output will have a totally different actually data type in this case. Okay, now to do that I will introduce back, okay, what we did so far, which is something called lambda expressions. Okay, now lambda expressions are used to, or could be used to define anonymous functions that do not have a name. Okay, now please take a look at the pattern. I will write something of the following form: \x, okay, meaning my function will be having as a parameter x, and what this function actually does is just actually takes the x and checks whether x is greater than 0 or not. And I will do it with the value 6, meaning I will be applying this function, okay, on 6. Okay, thus 6, is it greater than 0, yes or no? It's yes. That means you get actually true in this case. If you will do it with -6, okay, what you will get here is you will get actually an error, because actually the -6 will be considered to be a function that will be applied on a parameter that returns a function that expects another let's say function and another value in this case. And that's why here I see, okay, the mistake is that I have actually to put the -6 between brackets. That's in this case actually you get false as a result. Okay, now look what I can do now with the map. I can combine the map 2 with, let's say, a function that I will be defining as an anonymous one, x, where x is greater than 0, Okay, and last but not least, I will be having 1, 2, 3, minus 22, 66, and minus 1 in this case. Now 1, 2, 3, okay, the three values are positive, okay, and that's why I should get true. The minus 22 is false. The minus 1 is false actually because, the value of x greater than 0 will be false, since actually I'm having negative values in this case. And once you will run it, you will be getting as a result true, 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 false, true, and false. And this shows, let's say, the data type of the map 2. Okay, thus it's just take a look at the list. It's a list of here numeric values, and the result is a list of Boolean data types in this case. Okay, and here you see now how I combined, let's say, lambda expressions to define anonymous functions, just to perform an operation on every element using actually the map 2. Okay, thus just to repeat, what we were actually doing here is just to take a look at the pattern that is performed in this case. Okay, and here the pattern is almost the same, except, let's say, the application of the functions on every parameter that I'm having in the list in this case. And that's why the map function is the one that can be used in Haskell to perform this operation. Just for information, map is already predefined in the prelude, and that's why I defined it here as map2. Okay, now let's think about the following. I want actually to have as an example a list of the following 4, 1, 2, 3, 4. Okay, and I want actually to keep only the values that are having a value greater or equal to 3. Thus, in this case, the result should be 3, 4. If I have a list that consists of 1, 2, 1, 1, 0, then the result should be an empty list in this case. I want actually to define actually something, okay, that will check. Okay, I will call it remove elements from a list. Okay, and the element that I am removing should be element that are, I said, smaller or equal to 2. I keep only the ones that are strictly greater than 2 in this case. Okay, thus I will just write remove an empty list is equal to an empty list. Okay, and then I will remove. Okay, I will call it remove all, okay, x and xs. Now the question is, which element should I keep? I will have, and which element should I remove? I will have actually an if condition in this case. Now, if my x is strictly greater than 2, I will keep it. Okay, then the result will be x, okay, colon, and then what I will have here is a remove all, okay, of xs. Okay, else the result will be I will not include the x, but I will remove all from xs in this case. Okay, you go and you try actually to run it, and then if I am having a remove all of for example a list that consists of 1, 2, 3, 4, you get as a result 3, 4. If I am having a list that is having 1, 2, 1, 1, 1, 0, and minus 5, the result will be an empty one. Why? Because I will be taking the elements one by one. Okay, and I will keep them if the element is strictly greater than 2, and I will remove them if the condition is not true. After removing elements that are strictly greater than 2, we want now to remove all numbers that are even. Okay, now to do that, we will check the following. We want actually to check whether x is an even number or not. and that's why I will perform the operation mod x2, okay, equal to 0. Okay, let's check it. Okay, I will just compile and I will check even 8. 8 is an even number, you get true. Even 7 is an odd number, you get actually false in this case. Thus, let me implement the remove all even. Okay, please take a look at this function, which is the remove all elements that are strictly or less than or equal to 2, and keep all elements that are strictly greater than 2. Thus, what I will do is I will remove all even numbers. Okay, in this case, what I will do is I will write the following: remove all even. Okay, an empty list is equal to an empty list. Please actually look at the base case. The base case is identical. Okay, and now what I will do is I will have remove all even. Okay, or remove all odd. Let me change it in order here to have, let's say, the same pattern as the one here. That means I will keep all even numbers and I will remove all odd numbers. Okay, thus I will be having XS, and what I have to do is I have to go and check every element one by one and check whether this element is even or not. If it is even, I will keep it. If it is odd, I will remove it. Okay, how will it happen? Same way as it was actually done here. Thus, I will write the following: if even x, then I know exactly I should keep it. Then I will have x cons and then remove all odd xs. Okay, and then if it is not the case, then I will be having an else statement where I will not keep the x, but I will remove it, and after that I will remove all odd numbers from xs in this case. You see actually the pattern is almost the same. Once I will run it ambiguous, it has to be called even 2 because even is already predefined in Haskell. Okay, thus once I will compile, this one will give me a nice result. If I want to remove all numbers that are odd, if I will be having 1 2 3 4 5 6, okay, I will be keeping the 2, I will be keeping the 4, I will be keeping the 6, and the 1, the 3 and the 5 will be removed in this case because all these numbers are odd in this case. Okay, now what I want to do is I want to implement a higher order function. The higher order function will be called actually filter. I will call it filter 2 because there is already a function predefined in the prelude which is called filter. This function takes a predicate p, and what it does is it just actually perform almost actually the same operation that I am seeing here. Okay, however, the p is now a generic predicate, a generic constraint that you have to check. If this predicate is true, then what I will do is I will keep the element. If the predicate is wrong, I will remove it. Thus the filter p will be defined as follows. Okay, if let's say the list is empty, then the result will be empty in this case. And if the list is not empty, the same actually pattern. Now like remove all and remove all odd. Okay, however, now the p is a generic one. I will be doing it with x and xs, which is a list that consists of at least one element, and then I will be having the same thing. If p of x, meaning if p of x holds, then what I will do is I will keep the element and I will, let's say, filter all elements from the xs. Okay, otherwise what I will do is I will not add the x, but I will go and filter to all elements with p from xs in this case. Okay, and the nice thing is once you will run it, now what you can do is you can actually think about the following: filter 2, then even or even 2. Okay, 1 2 3 4 5 6 7 8 9. Okay, we'll keep all elements that are even, or remove all elements that are odd. Now the first one, which is the remove all, can be now implemented as follows. Okay, I will write filter 2. Okay, I will keep all elements that are strictly greater than 2. This is my predicate. Greater, okay, takes a parameter. Okay, it returns another function that expects another parameter, and the whole value will be of type actually Boolean in this case. Filter 2 greater than 2. And what I will do is I will do it with 1, 2, 3, 4, minus 22 and 33. Okay, what I will keep here is I will keep the 3, I will keep the 4 and the 33, and the 1, the 2 and the minus 22 will be removed actually from the list. Okay, nice. Now the nice thing is once I have that, then the remove all 2, okay, I will implement it actually as follows. It takes actually, I'm sorry, it takes actually a list L, and what it does is it calls actually the filter 2 with P, okay, which is in this case the greater 2, and what it does is it does it actually with the L in this case. Okay, now once we have that, you will see now a remove all and a remove all 2, shorter, more concise than the one that I'm implementing here. Why? Because I'm relying on a higher order function, which is a function that takes as a parameter another function. One of the parameters is a function in this case. Okay, now look, once I will go here and I will load. Okay, now instead of calling a remove all, I will be calling a remove all 2. Okay, and the remove all 2 will have 1, 2, 3, 4 and 0. The 3 and the 4 will be kept, the 1, the 2 and the 0 will be removed. And just actually to do it in a nicer way, the remove all, since I'm using currying, I don't need actually to pass the parameter, because you see the parameter here actually to the right. And now once you will do it, once you will go and you compile and you call the remove all, you get actually the same result, and you will be seeing here a difference between the remove all, where you have to implement your base case as well as the recursive case, okay, and the second one where you will be relying on a filter function, which is a higher order function in this case, and the functionality of both functions will be the same. Okay, now let me go to the filter and let us actually think about the type of the filter. Okay, that's I will write here type of filter 2. Okay, I will do it step by step. As we saw before, you get filter 2p, okay, and then here you are having a list and it's equal another list. That means actually what I can say is only that I will be having something of the following form. A implies, okay, then B implies C. This is actually the general pattern. Now once I will dig actually to this parameter, then this one has to be of type a list of B's. And once you go and you take a look at the output, then you know exactly that the output is of type list of C's in this case. The first definition doesn't tell me anything whether the type of the list, this one is this of the elements of this list is the same as the type of the elements of the result list. Okay, this is what I get just by analyzing the first one. Now let me go step by step actually to the second one. I will be seeing filter 2p x colon xs. Please actually forget actually this part. Okay, with this one I will not be able to change anything because I am not having any additional information. Now the nice thing is I will be seeing if p of x. Now if I am having if p of x, I know exactly that the x is coming actually from the list, okay, which is actually of type, or where the elements are of type b. And since I am having if p of x, I know exactly that the p is a function that should return true or false. It's a predicate. Okay, that I know exactly that this one should be of type a, implies, I'm sorry, here a Okay, it should be A. Implies Boolean data type. Okay, this is, let's say, the data type of this one. However, just by looking at, let's say, the parameter that P takes is a parameter X. Well, I know exactly X is an element of the list, and the list is of, let's say, elements of type B's, and that's why I know exactly this one has to be of the same type. That means you are having B implies Boolean, implies a list of B's. Now the only question is, this list, is it actually any list, or does it have actually to be of the same type of the data type of the input list in this case? Now once you see how the list, which is the result list, is generated, okay, you will know exactly that the X will be const actually to this, to the filter, to the recursive call of the filter. That means I will know exactly that this list has to be of the same data type. Okay, thus once I will go and ask about the filter of 2, you get actually, let's say, the same pattern. It's actually B. Okay, here it's actually, I'm having it with the variable A. A implies bool. Okay, implies a list of A's, implies a list of A's in this case. Okay, and again, once you will just compile this one, and you want actually to filter with for example odd 1 2 3 4, okay, you see that actually the odd is a predefined function, the filter is a predefined function too, okay, and that's why if you do it with the filter 2, this one will work in this case without any problems. Okay, is this part clear for everyone? Yes or no? Okay, hopefully we don't have a problem with the filter, okay, nor with the map. Okay, now let's go to the last example. The last example is about the following operation that I want to perform in Haskell. Okay, now I will just actually give you the pattern. I will want to define something that will perform the following operation. I get 1 2 3 4 as a result, and I want to perform the addition of all values of this list, meaning the result in this case should be 7 plus 4 plus 3 plus 2 plus 1, or 1 plus 2 plus 3 plus 4. You will be having 10 as a result. Okay, thus it's called sum all. Okay, thus the sum all, if the list is an empty one, then the result is 0. The sum all, if the list is not empty, what I will have as a result is x plus, and then the sum all of xs. Okay, as simple as it is. Once you will go, you will run it. Okay, the sum all multiply is already predefined here. Okay, I will write add all, okay, and add all. It's just actually the summation of all values. Now once you will do it, once you will load, and you get add all of a list that consists of 1 2 3 4, I'm having 10 as a result. If you do it with, let's say, -1, you will be having, in addition to it, in addition to the list -1, you will get actually 9. If you do it with the list which is an empty one, you should get actually 0 as a result. Okay, now let's take a look at another one, and let's compare it to the add all. I want actually to perform the multiplication, meaning if the list is 1 2 3 4, okay, the result should be the result of multiplying 1 times 2 times 3 times 4, meaning in this case you will be getting 24 as a result. Okay, now the question is how will it work? I will have the following, its product all. Okay, if the list is empty, then please take a look at the following. The only difference is that actually the result will be equal to 1. Okay, because you are having, let's say, the product is not, let's say, the addition, and that's why you will be having as a result, if the list is empty, then the product will be equal to 1. However, if I will have a list which is not empty, okay, in this case xxs, then what I will do is I will get as a result x, and this same actually thing, except instead of performing the addition I will be performing the multiplication, and then you will be having product all xs in this case. The pattern will be the same. Once you will go, you will run it and you will perform, let's say, the product all of this list. Okay, what you will be getting here is minus 24, because 1 times 2 times 3 times 4 is 24, times minus 1 will be equal to minus 24. If you remove this one, it will become 24. If you will add 0 to it, it will become actually 0 as a result. Okay, that's the question is, what are the things that looks actually the same, and what are actually the things that look a little bit different in this case? Okay, now the pattern is the same. The result depends on the operation that you will be performing. Here I will be having 0, here I will be having 1. Okay, now, and the operation that I am performing is different too. Here I will be performing the addition of plus with the plus, and here I will be performing the operation with the times. And that's why what I want to do is I want to implement a function. In Haskell, it's called fold R2, that takes now, let's say, a function. This is the function that I will be applying on my list. It takes as another parameter the e, which is actually the base case. It could be 0 if I am adding all elements of the list. It could be 1 if I am performing the multiplication of all elements of the list. Okay. And last but not least, I know exactly if the list will become empty, then the result is not always 0, is not always 1, but it depends on the input in this case. Thus, the result will be equal to e. Okay? Now, I will go further, and I will go to the recursive code. Fold R2 of A, F, E, and the list that consists of 2 elements. At least 1 element, x colon xs, where the x is the head and the xs is the tail. Now, what will be actually the result? The result is that I will be taking f and I will apply f on 2 parameters. The first parameter is the x, and the second parameter is, let's say, the result of performing the fold R2 of f e on xs in this case. Thus, this function will be taking as 1 parameter the first element of the x. Okay, it returns a function that expects as a parameter the result of performing, let's say, the folding, okay, of the tail list with the same function f, however, in this case with the same base case e. And I will stop whenever actually the e will be equal, or whenever my list will be equal to an empty list in this case. Okay, now I will go and I will compile. Okay, and what I will do is I will just actually call the fold R2, okay, of an f, which corresponds actually to an addition. Okay, LE will be equal to 0, and the list is 1, 2, 3, 4. That means what I am doing here is I'm simulating an add all. Okay, the result will be 1 plus 2 plus 3 plus 4. Okay, and if I will do it with the multiplication, you have to take care. What I will change is I will change the function, and what I have to do is I will have to change actually the base case. Okay, and the result will be equal to 24, which is the multiplication of 1 times 2 times 3 times 4. Okay, let me go to the fold R2 plus, and let us actually see how the evaluation is done. Okay, now I will do it step by step. If I call fold R2 of plus, and now 0 and 1, 2, 3, 4, okay, this is exactly what will happen. Okay, the list is not an empty one, and that's why I will be going to the recursive call. It's f of x, where the f is the addition, meaning I will be having, in this case, x, which is 1, plus, let's say, something that will be done recursively. It's fold R2 of 0 and a list that consists of 2, 3, and 4. Okay? Thus, the whole thing will be called recursively. I will be having 1 plus, and then what I will be doing here is fold R2 of 0, 2, 3, 4. Okay, it doesn't match with the first case, but it matches with the second one. And the second one, my function f is here the addition. Okay, that's the addition. Actually will be cap. It's plus. Okay, 0, 2, 3, 4. And that's why what I will be getting here is I will be getting 2 plus, and then the recursive call of fold R2 of plus 0 and then 3 and 4. Okay, now we are actually folding, okay, from the left to the right, and the result in this case will be 1 plus 2 plus, okay, now fold R2 plus 0, 3, 4 doesn't match actually the first one, but it matches the second one. The f is the addition. The addition expects actually 2 parameters. Instead of writing it now in prefix notation, I will write it as before in infix notation. That means I will be having 3 plus, and then the call is fold R2, the same operation, plus 0, and last but not least 4. Okay, and now what will happen in this case? Okay, I will go to 1 plus 2 plus 3 plus, and now fold R2 plus 0, 4 doesn't match actually the first pattern, but it matches the second one. I will be getting 4 plus, and then last but not least I will be having fold R2. I will be having the plus as an operation to be performed. The 0 is, let's say, the base case whenever actually I reach an empty list, and I reached it now. That means the whole thing will be performed as follows: 1 plus 2 plus 3, okay, plus 3 plus 4. And now let's go actually to the last one. Fold R2 plus 0 empty list will match actually this pattern. The result will be equal to 0. Okay, and the result will be in this case equal to 10, as you will see here. Okay, nice. Let's take a look at the type of fold R. Okay, and let's do it step by step. And here you have to focus a little bit. Okay, now the question is what will be, let's say, the type of fold R. Okay, I will just comment it, and the fold R is having, let's say, take a look at the first one. Okay, I will start one by one. The first F, okay, it's something of type A. The second here is E. The E is of type B. The third one is a list. Okay, the list, Allahu Alam, what kind of elements will it have, is actually something of type C. And last but not least, if I am having here E, I know exactly that actually this is the same value. That means since I am having here B, I will be getting actually B in this case. Okay, that's, I hope it's clear. Now I will be having the following pattern, which is not actually the final one. F is of type A. B is of type E. The empty list is a list of type C's. Okay, and the E, okay, since it was here of type B, then actually the result will be of type B in this case. Okay, now the question is, can I make actually that type more specific in this case? I will take a look at the recursive case. Now the first one is done, and I will take the look at the left hand side. The left hand side will not tell me anything, okay, additional to the type that you see here. However, once I go to the right hand side, okay, things will become clearer. I know exactly that the F is taking as a parameter X. This one will return a function that takes as another parameter the result of fold R2, F, E, and XS. And that's one, this one should be actually something of the following type. F is applied on X. The X is of which type? The X is of type C. Okay, now this is the X. It returns actually something of a function that will be applied on the result of this one. And I know exactly that this one is of type E, because this is actually the return value of the base case, meaning this one is C implies B. Okay, and the whole thing will be returning something that should be of the same type as the first case, meaning this one actually has to be of type B in this case. Okay, and now I will go and take a look at the type of fault R2, and you get actually the same data type. Instead of the C, you are having an A, thus you are having A implies B implies B. This is actually the data type of the F. Okay, then you will be having the B, which is the data type of the E, and last but not least, you are having a list of A's, which is the data type of the list X colon XS, and the result has to be of type B. Why? Because actually here the result is E, that means actually it has to be of the same type as the base case in this case. Okay, now let's go and think about using a fault R2. Now the question is, if I am having a list of the following four, 1, 2, 3, and then 4, 5, 6, okay, and last but not least, I will be having a list, okay, 9 and 10. What I want to do is, I want, without actually thinking about how the whole thing will be implemented recursively, but using the functions that we defined before, we want actually to think about a function that will flatten these lists to get as a result 1, 2, 3, 4, 5, 6, and 9, 10 in this case. Okay, now I will call it flatten list. Okay, it's a list L. Okay, and now which operation do I have actually to take? It's not a mapping, it's not a filter, meaning in this case I can do it with the fault R, let's say 2. Which operation do I have actually to do? I have to take the parameters one by one, okay, and perform a kind of append actually for it. The only thing that I have actually to do is just to write what will be actually, let's say, my base case scenario. Okay, whenever actually the list will become empty, then actually the base case is that the list is empty too, and then you will be having L as a result. Okay, now look, once you will go and once we will compile, okay, this one actually will compile correctly, and then once I will be having a flatten of list, okay, of a list that consists of 1, 2, 3, and 4, 5, 6, okay, life will be good, and the result will be actually the flattening of the list in this case. Now the question is, what is the type of flatten list? Okay, I know exactly that it's a list of lists. Okay, it has to be a list of lists because actually here I'm appending all elements of the input list. This can only work if, let's say, the list which is the input list is a list of lists, and the result will be a list of parameters of, let's say, the nested lists in this case. And that's why here, if I will write it, then actually the flattened list should be of the following type. It's a list of A's, okay, and what it gives you here is a list of A's, okay. And if you will ask about actually the type of the flattened list, then you will see it's actually the same one, okay, because I can take this one and convert, let's say, this one to 1 and 2 and 3, and last but not least you will have this one as, let's say, GUC and hello, okay, and the result will be actually a flattening of all lists in this case. Okay, currying, what I have here is a flattened list of L, and here I will be having fault R2 plus empty list and L. That's what I can do is I can remove this one in order to have it in a more, let's say, concise and in a shorter way. That's once I will do it. If I will go, I run, okay, and I compile and I do the flattening of the list, you get actually the same result. Okay, just actually keep in mind, the fold R2 performs an operation, in this case, from, let's say, the left to the right. Okay, think about one where actually the operation will be done from the right to the left, which is actually a predefined one, which is called fold L. Try to implement it yourself. However, the operation shouldn't be 1 minus 2 minus 3 minus 4. Okay, but in this case I want actually to perform the operation as follows. It's a fold actually from the left. The result should be 0 minus 1 minus 2 minus 3 minus 4. You won't see a difference if you will do it with the plus, okay, because the operation is the plus actually is a commutative one. However, the minus is a left associative operation, and that's why using fold R or fold L should or will give you actually a different result. In this case, the result here should be 0 minus 1 minus 2 minus 3 minus 4, which gives you actually minus 10. Try to do it at home. Try actually to think how the whole thing will be implemented. The objective of the lecture was to introduce for you higher order functions that will simplify your life whenever you want to implement some of the functions that are having a specific pattern. Okay, and that's why you have always to think of using either map to perform operations on every element of the list. Filter if you are having an operation that removes, let's say, some of the elements from the list. Or fold R, fold L, that performs actually operations on the elements of the same list. Thank you very much, and see you next week, inshallah, okay, for the next lecture. Assalamu alaikum, and stay safe. Stay home. Bye bye.